Hello, and welcome to the Radcliffe Institute for Advanced Study at Harvard. My name is Claudia Rizzini. I'm the Executive Director of the Fellowship Program. The Radcliffe Institute brings together students, scholars, and practitioners from across disciplines and professions to create and share transformative ideas. You can participate in these laboratory ideas by attending public programs such as this one, visiting virtual exhibitions, or pursuing the special collection held at the Schlesinger Library. To learn more about Radcliffe, please feel free to sign up to receive information on news and events at radcliffe.harvard.edu. We'll begin the program with a presentation by Professor Paul Martini. After the presentation, the speaker will respond to questions from the audience. Please use the Q&A feature on Zoom to submit your questions at any time throughout the program. We ask that you keep your questions brief to allow us to address as many as possible in the time that we have together. Now it is my pleasure to introduce this year William Bentinck Smith Fellow Paul Martini. He is a professor in the Department of Astronomy and member of the Center for Cosmology and Astroparticle Physics at Ohio State University. Professor Martini is an astronomer with triple expertise. He builds instruments for astronomical telescopes, he executes ambitious and systematic observational programs, he constructs insightful theoretical models to interpret observational data. As a student at Ohio State University, he worked on a seminal paper, Martini and Weinberg 2001, on the clustering of quasars, the most luminous objects in the universe. The paper has since been cited over 250 times, establishing Professor Martini as a leading expert on the fueling and lifetime of quasars, and on the connections between quasars and their host galaxies. As a principal investigator in the Astronomy Instrumentation Laboratory at Ohio State, he built a multi-object spectrograph used to answer fundamental questions in astrophysics and cosmology. This spectrograph was so efficient and cost-effective that the National Optical Astronomy Observatories contracted with Martini to build two more for the US telescopes in Arizona and Chile. Professor Martini's most important contribution to date is his work over the last several years as instrument scientist of the Dark Energy Spectroscopic Instruments, or DESI. DESI is an international project led by the US Department of Energy to build the most powerful survey spectrograph ever constructed. The plan is to use the spectrograph to create a three-dimensional map of the cosmos that will be 10 times larger than those existing today. In his role as instrument scientist, Martini helped to set the direction and oversee the efforts of nearly 100 scientists and engineers working on the project. Martini has been a visiting professor at the University of Virginia and visiting astronomer at the National Radio Astronomy Observatory in 2012 and 13. Prior to joining Ohio State, he was a Clay Fellow at the Harvard-Smithsonian Center for Astrophysics and a Carnegie Star Fellow at the observatories of the Carnegie Foundation for Science. Martini earned his PhD in the Department of Astronomy at Ohio State University. At Radcliffe, Paul is working on analysis tools and data from DESI to address the mystery of cosmic acceleration. The most prevalent view is that a cosmic acceleration is due to some negative pressure associated with the vacuum of space, commonly referred to as dark energy. Paul plans to measure the statistical properties of the expansion of the universe and growth of structure over cosmic history, which contains key information about the physical explanation. He will use this data to test the leading hypotheses for the origin of cosmic acceleration, such as dark energy and modifications to general relativity. And now it is my pleasure to give the virtual floor to Paul Martini.
Thank you, Claudia, for that generous introduction. As a fellow at the Radcliffe Institute, I plan to study the nature of cosmic acceleration with the new scientific instrument called the Dark Energy Spectroscopic Instrument, or DESI. As Claudia mentioned, I've helped to build DESI over the last 5 years, and I'm excited to tell you why we built it. And I'm especially excited because DESI is at the cusp of beginning a new survey of the night sky that should dramatically surpass similar projects. I chose this background image for my title slide for two reasons. One is that it captures the impressive structure that houses the telescope. DESI uses the largest telescope at the Kitt Peak National Observatory in Arizona, the 4-meter Mayall telescope, and it appears to tower over both other telescopes and even nearby mountains. Another reason is that this photo captures some of the beauty of the sky at night. One of the most romantic aspects of astronomy is spending the night at a telescope, usually at the top of a mountain in some very secluded location, staring up at the night sky and pondering the sheer size of the cosmos relative to our very small place within it. This contrast is humbling, no matter how impressive the telescope and mountain may be. To better capture this point, I'd like to share with you a small anecdote about the immensity of the universe. You may have heard of the New Horizons mission to Pluto, which was launched in 2006. At the time, New Horizons was the fastest spacecraft ever launched from the Earth. When it flew by Pluto, 10 years later, it was traveling at 32,000 miles per hour, or a little over 14 kilometers per second. That is amazingly fast. Yet at this speed, it would take nearly 90,000 years to reach even the nearest star. And the objects that interest me are millions to billions of times farther away than that. Yet it was neither the beauty of the night sky nor the vastness of the universe that attracted me to astronomy. Instead, I was attracted by the possibility that we can use astronomical observations to study physics and to answer questions about the universe, even though the objects we study can be millions to billions of light years away, and therefore they must have emitted their light millions to billions of years ago. One early, very relevant application of using astronomical observations to study physics is Edwin Hubble's discovery that more distant galaxies are receding from us more rapidly. This figure shows the key result from Hubble's work, which was published in 1929. The bottom axis shows the distances to various galaxies in his study. Astronomers commonly measure distances in parsecs, which corresponds to a little bit more than 3 light years. And for context, that nearest star to the Earth is a little bit more than 1 parsec away. The galaxies on Hubble's diagram, indicated by the points, are at distances of up to 2 million parsecs. These are already huge distances, much larger than our entire galaxy. The vertical axis is the recession velocity in units of kilometers per second. These range up to about 1,000 kilometers per second. These are also huge velocities, much faster than New Horizons' speed of only about 14 kilometers per second when it passed Pluto. The light waves from objects moving away from us are shifted to longer wavelengths by the Doppler effect. This is similar to how sound waves from a siren speeding away from you will be shifted to lower frequencies. Because red light is the longest wavelength electromagnetic radiation visible to the human eye, astronomers say objects moving away from us are redshifted. The key result of this figure is that more distant objects are more redshifted than nearer objects. This figure shows that the redshift is proportional to the distance, and this means that the universe is expanding. To help picture why this is the case, imagine the 3D universe as a 2-dimensional sheet. Of course, this is just an approximation, just like you can only see me in 2 dimensions right now, even though I am quite sure I am actually 3-dimensional. So imagine the universe as a stretchable sheet with galaxies painted on it, and then stretch your sheet in your mind to make the sheet larger. Here's a visualization to help. The bottom of the slide is supposed to represent the start of the universe's expansion, nearly 14 billion years ago in the Big Bang. Then the 3 subsequent layers are later snapshots in the evolution of this 2-dimensional version of our universe. At each time, the sheet has expanded. The distances between neighboring galaxies have steadily increased, and the further away galaxies were initially, the more they have moved apart. Since more distant galaxies have separated by a greater amount, they must also be moving apart more rapidly. And that is why there is a relationship between distance and redshift. Now I will go back to Hubble's diagram to emphasize several important aspects of it. The first is that the relationship between distance and redshift is really not overwhelmingly obvious. In statistical terms, the data are pretty noisy. One reason for that is that the measurements were hard to make. The observations Hubble used were obtained with photographic plates, which were not as sensitive as modern detectors, and they were much, much harder to calibrate. Another is that 2 million parsecs is really not a big sample of the universe, even though light from that distance has been traveling to the Earth more than 10 times longer than the oldest fossil evidence of our species. At small distances like these, the redshift measurements are affected by the random motions of galaxies, in addition to the expansion of the universe, and they only sample a very small fraction of the entire age of the universe. The second part that I want you to note is that this diagram only has about 30 measurements on it. In the 91 years since this figure was published, the relationship between distance and redshift has remained a fundamental tool of cosmology. The slope of this relation is the expansion rate of the universe at the present day, and it is called Hubble's constant in his honor. Hubble's diagram demonstrated conclusively that the universe was not static, which until that time had been widely believed, although not understood. Many subsequent studies have used the distance redshift relation to estimate the age and the mass density of the universe, as well as other parameters. And now we use it to study cosmic acceleration. To picture how the distance redshift relationship can be such a powerful tool, imagine you're on the Earth, which should be easy, and that you throw a ball up into the air, which is also not too hard to imagine. If you throw a ball straight up, it is moving fastest just when it leaves your hand. That is the initial speed. Then as it climbs higher and higher, the speed decreases. In astronomical terms, the expansion rate is decreasing with distance, as well as with the time it is in the air. The reason it slows is almost completely due to gravitational attraction between the Earth and the ball, since we're ignoring air resistance. This is analogous to how we expect the expansion of the universe to decrease as the universe expands, because there is mass in the universe. If you were on the moon and threw the ball in the air with exactly the same initial speed, the ball would slow down more slowly because the force of gravity is weaker on the moon. There is less mass. The lower mass of the moon is why there would be a different relationship between the speed of the ball and its distance from you. Of course, on the moon, you also wouldn't have to worry about air resistance, although you would have to worry about breathing. This is why scientists like to use thought experiments like this when possible. They're usually safer than real ones and a lot cheaper. In the very local universe, where Hubble made his first measurement, he did not see a change in the expansion rate. This is because his data were not good enough to see the effect. But cosmologists knew the universe was full of matter, and they knew about gravity, so they expected to see a gradual slowing of the expansion rate if they could measure objects at greater distances and make more accurate measurements. There are two classes of methods that astronomers use to measure distances. One class is called a standard candle, and the other a standard ruler. The basic idea behind both the standard candle and the standard ruler are pretty similar, and both are illustrated by this picture. We identify some standard object whose intrinsic properties we know, such that when we observe them when they're at an unknown distance, we can figure out how far away they must be. For example, imagine we knew two candles were identical. If one of them appeared fainter than the other, we would know that the fainter one was farther away. And similarly for a standard ruler. If we knew a collection of rulers were identical, then we would know that the ones that look smaller, meaning that they have a smaller angular extent, must be farther away. Using very well-calibrated equipment, we can use these tools to estimate distances extremely well. Since we're measuring objects at astronomical distances, we need our standard candles to be very luminous and our standard rulers to be physically very large. Fortunately, pretty good proxies for both of these exist in nature. The standard candle that we use is a special variety of exploding star called a Type 1a supernova that can shine as bright as an entire galaxy, if only for a short period of time. And astronomers have detected them more than halfway across the universe. From careful measurements of how the brightness of these supernovae change with time, it's impossible to infer their distance. The standard ruler that we use is called the Baryon acoustic oscillation scale, and I'll return to that a little bit later. Before I describe some of the results of work with supernovae, however, let's go back to imagining that you are on Earth throwing a ball up in the air. We all know to expect that the ball will slow down as it climbs, and we know that the force of gravity is acting in the opposite direction of the ball's motion. Now, imagine you had thrown a ball up in the air, and instead of slowing down, it started to speed up again and fly away from you faster and faster. What would you say if this happened? If I saw this happen, I'd certainly have a hard time believing my eyes, as it violates the laws of physics I learned in school. Actually, I would have had a hard time believing this even if I hadn't studied physics. It is just hard to even imagine this happening. Yet amazingly, this is what cosmologists discovered that the whole universe is doing. Cosmologists used type 1a supernovae to measure the relationship between distance and redshift in the late 1990s and discovered that the current expansion rate is actually speeding up and not slowing down. This was a very difficult measurement to make because the size of the effect was small compared to the measurement uncertainties for individual supernovae. And the researchers knew that a result as extraordinary as the violation of one of the key laws of physics would need extraordinary evidence to convince other scientists. Nevertheless, the result was corroborated with 2 independent studies by 2 independent teams of researchers. Here is a summary figure that shows the results from both teams. They were the Supernova Cosmology Project and the High Z Supernova Search Team, combined with more nearby measurements from the Kalan-Tololo survey. This figure shows the brightness of supernovae as a function of redshift, combining the data from both teams. Because these observations extend well beyond the local universe, the redshift is now expressed as a fraction of the speed of light, rather than as a velocity. The individual points are individual supernova measurements, and the lines represent the expected relationship between brightness and redshift for different models of the universe. The lines in both panels, from the bottom to the top, show the expected relationship if there were progressively less and less matter in the universe. The less mass, the less the universe slows down. Mass is slowing down the universe. So more highly redshifted objects are further away and thus appear fainter if there is less mass in the universe. The data show that distant supernovae are even fainter than they would be if the universe had no mass in it at all, something we know is not the case. That means the expansion rate of the universe is accelerating rather than decelerating. And for this extraordinary discovery, 3 of the leaders of these teams were awarded the Nobel Prize in Physics in 2011. Measurements of supernovae, along with observations from other studies, have been used to continue to refine our best model for how the expansion rate has changed over most of the history of the universe. Now, I will show you how the prediction of how the expansion rate has changed that agrees with supernovae and other studies. This figure shows redshift along the bottom axis and the expansion rate along the vertical axis. I've also added the age of the universe along the top axis. We are presently at redshift 0, and the current age of the universe is about 13.8 billion years. Note that this figure only shows about the last 12 billion years of cosmic history, and not all of it. The expansion rate after 2 billion years had decreased to about 80 kilometers per second per megaparsec, and continued to decrease until about redshift 0.5, when the universe was about 8.5 billion years old. That was about 5 billion years in our past. This decline over much of cosmic history is exactly what was expected from gravity, the universe slowing down. The increase since that time, since about redshift 0.5, is cosmic acceleration. The expansion rate steadily rises to the present value, where it is a little bit less than 70 kilometers per second per megaparsec. This increase is the big mystery. What could be causing the universe to literally defy gravity? One immediate explanation is Einstein's cosmological constant. Einstein included a cosmological constant alongside his theory of gravity in 1917, because at the time, the widespread belief was that the universe was static. Einstein knew a static universe required something to counteract gravity, just like we know a ball won't float in midair without some other force. Einstein, however, threw out the cosmological constant upon the discovery of the expansion of the universe in the late 1920s. But the discovery of cosmic acceleration does require something to counteract gravity in a similar way. An important point I want to make, however, is that while adding a cosmological constant to Einstein's equation does successfully produce the acceleration, it does not say at all what the cosmological constant physically represents. So, what is it? Well, the short answer is we don't know. And that's why we built the DESI experiment. Somewhat longer answer is that there are a lot of really interesting and plausible ideas. Interesting because no matter what the explanation is, it is going to expand our knowledge of the physics of the universe. One proposed explanation is that there is some property of space itself that exerts a negative pressure that works in the opposite sense to gravity. In the language of general relativity, there is some intrinsic energy density associated with the vacuum of space that acts like a negative pressure. This is commonly referred to as dark energy, as, like dark matter, we do not see it. Although, unlike dark matter, it is increasing the rate of expansion, not decreasing it. But what is dark energy? There is a plausible route to an explanation with quantum field theory, yet estimates from quantum field theory overpredict the value of the cosmological constant by over 100 orders of magnitude, which is huge even by astronomy scales. This next figure shows an artist's conception of what the quantum realm might look like. This is, of course, only an artistic rendition of the quantum realm, because quantum fluctuations are only predicted to be present on such small scales that they're not directly observable. They are as small compared to individual atoms as the atomic scale is to us. How can we figure out what is causing the expansion? First, we need hypotheses that we can test with data, as that is the cornerstone of science. If an idea can't make predictions that are shown to be accurate, it is not elevated to a scientific theory. In the case of dark energy, there are two main hypotheses. One is that dark energy is a generic property of spacetime. That is, it is a true cosmological constant. This means that the more the universe expands, the more space there is, and the more negative pressure. This makes a very specific prediction for how the cosmic acceleration should change over time. The second option is that the dark energy is due to something else, like a new force of nature. We already know of four fundamental forces of nature: the strong and weak nuclear forces, the electromagnetic force, and gravity. So this hypothetical fifth force is commonly called quintessence. Many scientists have hypothesized that quintessence could explain cosmic acceleration. Unlike a cosmological constant, the impact of quintessence probably changes with time, and therefore these models predict a different distance redshift relationship from a purely cosmological constant. The third most prevalent explanation is that some modification to Einstein's general theory of relativity is necessary. This explanation proposes that gravity changes from being an attractive force to a repulsive force on very large scales, larger than even the several million light years of the largest galaxy clusters. This could also explain cosmic acceleration, and most importantly, makes very distinct predictions for how galaxies should move relative to other galaxies when they are at large separations. We can also test this hypothesis with observations of the universe. All three of these ideas are exciting, and we need more tools and more data to test them. At the moment, the best data we have comes from combining measurements of galaxies and quasars with supernovae and the cosmic microwave background. I'm going to focus on one specific tool, a standard ruler called the Baryon Acoustic Oscillation Scale, or BAO scale for short, as that is the main tool that the DESI project will use. The BAO scale is a relic from very long ago. only hundreds of thousands of years after the Big Bang. At that time, the universe was so hot and dense that light and normal matter were constantly interacting in what is called a photon-baryon fluid, where baryon is a word that describes most normal matter. One way to picture the universe at this early time is to try to picture the interior of the sun, except that this was what the entire universe was like. After you think about this for a little bit, you will probably be glad that we're actually about 93 million miles from the sun. While the universe was so hot and dense at that time, waves were propagating through this fluid of a mix of normal matter and photons, somewhat similar to the way that sound waves travel through the air. And that's why these are called baryon acoustic oscillations. All of these waves traveled at the same speed and traveled until the universe suddenly became low enough density that the photons and baryons decoupled from one another, and then the waves stopped propagating outwards. This happened about 375,000 years after the Big Bang. These waves left behind a very slight excess of normal matter at a separation of about 150 million parsecs from all other excesses of matter, such as galaxies. And then the photons drifted off and became, or streamed away and became the cosmic microwave background. There are three facts that make the Bao scale such a useful one for cosmology. The first is that we can measure it very precisely with the cosmic microwave background. And that's what's illustrated on the left of this figure, the cosmic microwave background here, and a circle to indicate a wave the size of 150 million parsecs across. The second is that the Bao scale hasn't changed since that time, since 375,000 years ago. So it is truly a standard ruler. And the third is that this ruler is huge. 150 million parsecs is really, really large. However, there's a disadvantage to it too. The Bao scale requires a lot of measurements to detect, and it was only detected for the first time in 2005, when two teams published independent results, one using a sample of 50,000 galaxies, and the other with over 200,000 galaxies. Both of these are huge samples, but that is just what was necessary to detect this cosmic ruler. Over the last 20 years, the largest spectroscopic survey project to measure these enormous numbers of galaxies has been the Sloan Digital Sky Survey, or SDSS, which uses this 2.5 meter telescope in New Mexico. As of this year, SDSS has measured over 3 million redshifts, which took about 2 decades. SDSS has managed to do this because they observe many objects at the same time, up to 1,000 at once. They use metal plates that are custom drilled with up to 1,000 holes to match the pattern of galaxies and stars and quasars that have been chosen for study. Then a scientist aligns a fiber optics cable in each drilled hole, and then the other end of that fiber optics cable directs the light into a spectrograph where the data are recorded. This figure shows an SDSS scientist aligning fiber optics cables with one of the plates. To observe over 3 million redshifts in this way requires many, many thousands of these plates, and observations with these plates, of many of these plates, every night for about 2 decades. With these millions of redshifts, the Sloan survey has reached back to measure distances to objects over most of cosmic history. This figure shows the measurement of the Bao scale in 7 samples of objects from the local universe to beyond redshift 2, where redshift is along the bottom axis. And the vertical axis is the ratio of the SDSS distance measurement to the best model prediction with a cosmological constant. The small panels show the slight excess that represents the baryon acoustic oscillation signal in each of the samples. The data very strongly support cosmic acceleration. While they do not show evidence for time variable dark energy, nor for modified gravity, absence of evidence is definitely not evidence of absence. we need much more data to test these hypotheses. And that is why I and a few hundred other scientists and engineers have worked to design and build the Dark Energy Spectroscopic Instrument. Our aim is to measure the Bao scale with about 10 times as many galaxies and quasars, 35 million of them, and to complete the survey in only about 5 years, rather than 2 decades. DESI will do this with the Mail telescope that I showed on my first slide. Here is what it looks like inside of the dome. The Mail telescope is a 4-meter diameter reflecting telescope. That means that the primary mirror is 4 meters in diameter. The primary mirror is located about here. And when light reflects off of this, it is directed up to the focus of the primary, called the prime focus. And that is where we place our instrument to collect the light from the telescope. The DESI project has added a lot of instrumentation to this telescope in order to complete our survey. And here is a model of the telescope that summarizes our additions to this project. Some of the highlights are that we built a new state-of-the-art corrector lens system with meter diameter lenses that give us a really large field of view. This corrector system then focuses the light from the primary mirror onto lots of fiber optics cables that transmit the light into 10 thermally controlled spectrographs down long fiber optics cables. 2 critical features are that we can obtain spectra of 5,000 objects at a time, and we have automated the fiber positioning process. We're no longer using drilled plates, so we can switch to new targets more rapidly. These last 2 points are particularly noteworthy because they enable us to observe a larger sample and to do it more rapidly. The key technology behind these points is what we call a fiber positioner robot. Here is what one of them looks like. The purpose of this positioner is to position a fiber optics cable at exactly the right place relative to its neighbors so that they all collect the light of distant stars, galaxies, or quasars. They are pretty small, similar in size to a pencil, and the tip of the fiber cable is pointing out from the end. They have to be small, so we can fit 5,000 of them into our instrument. The photo shows just one of them, and then the figure in the upper left shows what a photon of light would see as it approached the positioner. They work somewhat the same way as a human arm, just a lot smaller. There is one 3-millimeter long arm segment that rotates about the central shaft, somewhat like the upper arm rotates about the shoulder. And then there is a second arm that rotates about the end of the first, somewhat like the forearm rotates about the elbow. The end of the fiber is then held at the end of the second arm. This pair of arm segments can position the end of the fiber cable anywhere within a 12-millimeter diameter circle. Obviously, the reach is a lot smaller than a human arm, although these positioners are accurate to a few millionths of a meter, and my hand is certainly not that steady. The great technology that enables this fiber positioner is very small motors. These are very small in order to keep the positioners small, yet they also have to be strong enough, that is, that they have to produce enough torque to move the fiber cable around quickly yet precisely. This technology was developed for applications such as insulin pumps, medication delivery systems, and surgical robots. And it just so happens to be great for astronomical instruments too. The 5,000 fiber positioners are organized into 10 wedge-shaped structures called petals, and each petal has 500 of our 5,000 fiber positioners. The photograph at the left shows one such petal, which includes all of the electronics to operate 500 positioners, whose tips you can see here in this triangle. The middle panel shows the bundle of all 500 fiber optics cables that extend from the fiber positioners into our spectrographs. This cable bundle is about 50 meters long. And the photo at the right shows the unit that we put in the spectrograph so that we can record the light from our targets. This is another area where we adapt technology from other fields. The fiber cable that we use is the same type of cable used in telecommunications, including to transmit this talk most of the way from my computer to your screen. This fiber was developed to transmit light signals extraordinarily well to minimize the number of expensive relay stations. The fiber works equally well transmitting light from distant galaxies and quasars from our positioners into our spectrographs, because light is light. A great new technology from telecommunications that we use is called fusion splicing, in which two fiber cables are melted together to produce one longer fiber cable that transmits just as well as if it had been one fiber all along. This was critical for DESI, as it enabled us to combine fiber cables built in the United Kingdom with fiber positioners that were built in the United States, without connectors that would have dramatically impacted our throughput. DESI is the first astronomical spectrograph to use this technology. I took these photos when this pedal was still at the Lawrence Berkeley National Laboratory in California back in 2018. All 10 pedals were installed at the telescope in the summer of 2019. And this photo shows the process of installing one of them. I really love this photo, as it looks like something out of a science fiction movie, perhaps a robot performing surgery on a recalcitrant piece of equipment. The surgery analogy is actually pretty appropriate, as this delicate operation positioned each pedal to somewhat better than the width of a human hair in the focal plane assembly. Once all 10 pedals were installed, all 5,000 fiber positioner robots were finally together. The next photo shows a side view of the ends of the 5,000 fiber positioner robots from the summer of 2019. The complete focal surface is about 3 feet in diameter, and this photo illustrates how closely the positioners are packed together. If you look closely, you can just see the change in the pattern at the boundaries of the 10 wedge-shaped pedals. The entire focal plane assembly contains over 500,000 parts and is housed in a thermal enclosure that protects it from outside dangers, including the arch nemeses of astronomical instruments, which are moths and humidity. Once the light enters the fiber cables in the focal plane assembly, it is transmitted through the fiber optics cables to the spectrographs. And I'm very excited to show you what the spectrographs look like, both because they're impressive too, and because I was very involved in building them in particular. This photo shows our 10 spectrographs in a special climate-controlled room at the telescope. There are many aspects of these spectrographs that makes them extraordinary, and in fact, our design for them has already been copied by other projects. One aspect is that these include special detectors that have superior sensitivity to nearly 1,000 nanometers, which is critical to measure redshifts for distant galaxies. Another is that each spectrograph splits the light of its targets into 3 wavelength channels, each of which is optimized for its wavelength range. This is a crucial part of our ability to detect faint objects. And a third is the use of high efficiency volume phase holographic gratings to disperse the light. A common theme of all these aspects is that every photon from our targets is precious. After all, they have traveled billions of years across the universe, and we want to make sure that they do not go astray in the last few tens of meters before we record them on our detectors. All of these technology aspects were critical to design and build an instrument capable of measuring 35 million galaxies and quasars in 5 years, 10 times as many as previous surveys, and in a fraction of the time those surveys required. I will now conclude with another look at the expansion rate of the universe, but now with forecasts for how well DESI will measure this quantity. This slide shows the same model for how the expansion rate varies with redshift that I showed previously, but I've now added forecasts for how well DESI will measure this quantity as blue circles with vertical lines that represent the expected uncertainties. These blue points exactly agree with the model because they are just forecasts. What really matters is the size of the uncertainties rather than the locations of the blue circles. In reality, the measurements that we obtain from DESI will be scattered somewhat within the range of those uncertainties. In contrast, the red squares with uncertainties are based on data. They are my estimates that were derived from the latest SDSS results. My estimates do somewhat undersell the results of that survey, as that survey measured many quantities about the universe that this figure does not capture directly. But my key point is that with DESI, we will be able to measure the expansion rate extremely well. I do want to emphasize that the evolution of the expansion rate is only one perspective on the evolution of the universe, and DESI and other surveys measure other important parameters too. These include the amount and distribution of dark matter, the growth of structure, and the sum of the masses of the 3 neutrino species. While I have focused on dark energy and cosmic acceleration, we do not know what dark matter is either, and measurements of how clusters and superclusters grow over time is an excellent probe of modified gravity models. While the DESI project was shut down in March due to COVID-19, we're on track to restart observations within about a week, and I'm very excited and grateful to be able to use my time at the Radcliffe Institute to study cosmology with data from DESI. In addition to thanking the Radcliffe Institute, I would also like to acknowledge the US Department of Energy and other agencies and foundations that have made the DESI project possible, and say that we are very grateful to conduct this survey from the land of the Tohono O'odham Nation. Thank you for your attention, and now I will turn the program back over to Claudia.
Thank you, Paul. Thank you for this really fascinating presentation. We do have questions, so let me get to the first one quickly. What do you think about the discrepancy between measurements of the Hubble parameter in the late universe versus that from the Planck CMB measurement?
Yes, so there is currently what's called the Hubble tension. This is a tension between the value for the local value of the expansion rate as derived from high redshift measurements using baryon acoustic oscillations combined with the cosmic microwave background with very local measurements that are done in a similar manner to the way Hubble did by using other ways of estimating the distances to nearby galaxies. And those are currently in tension with one another. And the latest results from the Sloan survey did bring them into somewhat better agreement than they had been before. However, there remains some tension between the two that indicates that either there is a problem with the local measurements or there is a problem with the cosmological model that is part of the fit to data from the cosmic microwave background and also the evolution of the universe's expansion history that comes from the Bao scale observations and supernova measurements. I think that there's possibility that there could be small aspects of both experiments that are the reason for the discrepancy. And I think that it is likely some source of systematic error is present in one or both experiments that would bring them into better alignment. But there's certainly a very intriguing possibility that this is yet another evidence that there is something fascinating about the universe that we have not yet figured out. With more data from these projects, from both the local measurements of the Hubble constant and the measurements we get from DESI, I think we should be able to answer that.
That's great. Next question. Do any other fields need the kind of robotic fiber positioners that we use in spectroscopy? Also, what is the limitation of integrated field units for the kind of work you are doing?
Yeah, that's an interesting question. So from the perspective of other areas of astronomy, there are other spectrographs that are that previously have been built, but then are being built today that attempt to create other robotic fiber positioning systems that are as compact and as efficient as the one for DESI. So far, none of them have as many positioners as DESI does, but there's active work going on now for the next generation of survey designs for thinking 5, 10, 15 years in our future for new spectrographs that could observe 5 or 10 times as many objects as what DESI is doing. With regard to integral field units, that's a way of obtaining not just a single spectrum of a galaxy, but obtaining spectra of multiple points of a galaxy at the same time. And that has a potential to tell us a lot of physical information about galaxies. One that's most relevant to my presentation is related to dark matter. We can use such data to obtain much better measurements of the individual masses of galaxies by looking at the motions of the population of stars within it.
Mm-hmm. How does the increasing numbers of satellites and other orbiting objects affect your astronomic research? And how do scientists negotiate with industrial and governmental stakeholders to manage orbital congestion?
Yeah, that's a great question. There is a great deal of awareness within the astronomical community that new satellite constellations that are being launched all the time, especially Starlink, do appear in astronomical images. This is particularly a challenge for imaging surveys, like, for example, the Vera Rubin Observatory in Chile is about to begin a large imaging survey of a large amount of the southern sky. And there will be a significant fraction of those images that have trails, light trails of satellites across them. And those obviously, or maybe obviously, corrupt the astronomical data. And we have to come up with ways to mitigate them. One way would be to try to work with industry to make the satellites darker so that they don't reflect sunlight into our telescopes. But I think so far it has been difficult to get a whole lot of traction on that issue.
Do you have a preferred hypothesis of the several that you mentioned for the accelerated expansion? Atmospheric distortion is always a problem. Do you do adaptive optics at the collection site or afterwards in post-processing?
Okay, so the first part of that question is about which of the three hypotheses I mentioned is my favorite. And I'm not sure if I don't think I have a favorite. I really would like to be driven by what the data show. I guess of the three, certainly the idea of there being a new force of nature that we haven't discovered is pretty appealing. I mean, that just seems very cool. It's certainly not every century that we discover a new force of nature. But then the idea that there might be a modification to gravity that changes it from being a attractive force to a repulsive force, I also find that attractive. And then let me see, the second part of the question was about post-processing or adaptive optics. So the Earth's atmosphere is turbulent, and that causes the objects that we observe to be spread out. They tend to make them physically appear larger than they otherwise would if we didn't have an atmosphere. Not that I don't like the atmosphere, but there are technological methods, including especially what's called adaptive optics, that uses either laser light or the light of stars to try to correct for these very rapid small-scale motions in the Earth's atmosphere. We don't use that technology in DESI. However, there are experiments that are developing that technology better. And the main driver for that is that if we can make our objects physically smaller in angular extent, then we have less background light that enters our spectrographs from the night sky or from the extragalactic light. And we collect, consequently, a better signal on the objects that we're studying. So it wouldn't surprise me if a next generation cosmology survey included adaptive optics technology. It's just very hard to get adaptive optics to work well over several degrees, which is about the size of the field of view of most of the experiments under discussion.
Mm-hmm. So we have a question, which is actually three questions. So I'll read them out one by one. How sensitive are DESI measurements to three models of dark energy you described?
Mm-hmm. That is a very difficult question to answer because there are not the predicted scale of the, say, quintessence force or the predicted scale at which gravity becomes repulsive is different for different models. So what we do have is about a factor of 5 or 10 greater sensitivity to these quantities than previous studies. And so we potentially will be able to tell the difference between a purely cosmological constant and a time-varying dark energy, or between a cosmological constant or other form of dark energy and modified gravity by our measurements. So if there is a large enough signal, we will be able to see this. But there is some significant uncertainty into how large any of these effects will be. It's somewhat like the anomalous precession of the orbit of Mercury. The orbit of Mercury was known to precess and to precess more than what was predicted based upon Newtonian gravity. This was a major problem in the 1800s that many mathematicians and physicists and astronomers were working on, trying to understand its orbit. And there was no one was able to really explain an extra 10% of the signal. It turns out that once Einstein developed general relativity, he showed, oh, well, actually general relativity also explains the anomalous behavior of Mercury's orbit. But it was only a 10% effect. But if Mercury had been farther away from the sun, then the signal would have been smaller. And so we don't, it's hard for us to predict how large the signal will be similarly for these other hypotheses. But we hope that our experiment will be able to tell them apart.
So what is the key aspects of your spectrograph that gives you new results?
I would say the key aspects are really the phenomenal throughput of the whole instrument. And by throughput, I mean the efficiency with which it collects the light of distant objects. One way to measure that is to ask what percentage of the light that bounces off of the primary mirror of the telescope actually ends up getting recorded. And for a typical astronomical instrument, that can be 20 or 30%. So something like 70 or 80% of the light can be lost. For DESI, we managed to capture a much larger fraction of the light, 60 to 80%, depending upon the wavelength, and that helps us more efficiently observe distant objects. Another aspect of it is the fact that we can observe 5,000 objects at a time, which dramatically increases our ability to survey the universe.
Right. The next question is, has there been any real detection of dark energy or dark matter?
Well, there is, it depends on, so I would say yes. Well, at least for dark matter, there is unequivocal evidence that dark matter exists. There is lots of evidence ranging from the expansion of the universe to the orbits of galaxies around one another to the motions of stars within individual galaxies, including our Milky Way. That's not the same as knowing exactly what dark matter is, because that's an unsolved problem, but there's absolutely overwhelming observational evidence that there is some form of matter in the universe. Actually, the dominant form of matter in the universe does not interact via electromagnetic radiation with itself or with normal matter, as far as we know. And that's why it's called dark matter, of course. With regard to dark energy, it is in principle possible that actually the acceleration of the universe could be explained by modification to general relativity. But at the moment, we do fundamentally see evidence for cosmic acceleration. And so dark energy or a modification to general relativity are the best explanations we have. And of course, could be both.
That's great. Given that DAISY represents such a huge advance over our previous capabilities, what do you think will be the most exciting discovery from DAISY?
That's an excellent question. I think we have a very good there's a really good track record in new large experiments that the discoveries that they ultimately make are, or at least a lot of the most surprising discoveries they make are not the ones that they were initially designed to address, or at least some aspects of what they end up finding were not at all predicted by the people who designed and built the experiments. Personally, I am really intrigued by the prospects for testing modified gravity theories. I think that will be really fascinating, and DESI will be able to do this extremely well with measurements of the relative velocities of galaxies that are in close proximity. Although by close proximity, I am thinking like an astronomer, and so I mean within tens of millions of light years of one another.
I think we have time for one last question. What kind of new computational problems need to be addressed to handle the large amount of data you will be collecting?
Oh, that's a great question, and it gives me an opportunity to highlight the huge amount of work by many scientists in two very computationally intensive areas. One is to take the data that we are collecting. We have three channels and 3 detectors in every one of our 10 spectrographs. So we have 30 detectors that we use to collect our data, and then we're collecting, potentially we're using these to collect 100,000 spectra a night, or something of that order, and turning these into well-calibrated spectra that we can then use to measure precise redshifts and also perform other detailed studies is a huge computational challenge, and that has been a major area of work by many people over the last even 10 years. And then we've also invested a huge amount of computational resources and a lot of just raw thinking power into coming up with the best ways to analyze all of these data. As I've alluded to a little bit throughout the presentation, a tool like the expansion rate versus redshift it's a conceptually straightforward way to describe how the universe has changed, but it's really a simplification of a much broader wealth of information that we get. We measure quantities like the dark matter density, we measure the sum of neutrino masses, we measure the growth of structure versus time, we measure the distribution of galaxies and quasars. All of these parameters and many, many more are connected with one another in our larger cosmological model. It ends up being a many, many dimensional parameter space to explore with literally millions of individual measurements. And that's a computationally very intense process to work on, and it's even been a very computationally intensive process just to develop the tools and to make forecasts such as those that I showed in my penultimate slide.
That's great. This is all we have time for today. So thank you, Paul. Thank you for this fascinating presentation. I also want to thank you, our audience, for the terrific questions. I hope you'll be able to join us for other Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. With that, thank you all very much again, and have a good day. Bye-bye.